Hi, my name is Laura Titolo and I'm a researcher at the National Institute of Aerospace. In this presentation, I'm going to talk about a technique to automatically generate guard stable floating point code. So as everyone knows, floating point numbers are widely used to represent real numbers in our computer programs. However, the main problem of using floating point numbers is the presence of round-off errors. These errors generate from the difference between the real number we want to represent and its floating point representation. And when these errors accumulate in our computation, we can get a very different result from the one we expected. In particular, when this round-off error affect the evaluation of the Boolean guards inside an if-then-else, we can get the phenomenon of unstable guards. In this case, the floating point control flow of our implementation can differ from the ideal real number specification we have in mind. This makes the gap between real and floating point results even bigger, and this can have catastrophic consequences in safety critical software. For example, we have found some evidence of unstable guards in a library developed by NASA for air traffic conflict avoidance systems and for the offensive of drones. And of course, this happened because writing correct floating point code is challenging because it's very hard to predict how round-off errors affect the results of arithmetic and Boolean expressions. So our solution is to design an integrated toolchain, which is composed by three formal methods tools. The first one is Precisa, which is a framework for the analysis of floating point programs. The second one is PVS, an interactive theorem prover, and the third one is from a C, a static analyzer for C programs. And this toolchain is able to generate and verify in an automatic way a floating point C implementation from a PVS real number specification. This floating point implementation is instrumented to detect unstable guards, and it's annotated with information about the round-off errors occurring during the computation. So to give you a high-level idea of how this toolchain works, we have that Precisa, the static round-off error analyzer is our first step. So given a PVS real specification, Precisa is able to generate a C implementation of this specification that is also able to detect unstable guards. Then this C implementation is passed to from a C, which is going to generate a set of verification conditions that can be checked inside the verification tool PVS. So getting a little bit more into detail, this is a real specification of a simple program P, and we can get its naive floating point implementation by simply replacing each operator with its floating point counterpart and by rounding each number and each variable to the closest floating point. As I said before, the guard x, y greater or equal than z may evaluate differently in real and floating point arithmetic. And if this happens, the difference between the real program P and the floating point program tilde P is going to be as large as 2 units. So to solve this problem, we have defined a program transformation called tau that replaces the guard in the conditional if then else with more restrictive ones. So given our example, we can replace the guard x, y greater or equal than z with this guard here, x, y minus z greater or equal than epsilon, where epsilon is a correct over approximation of the round-off error occurring in x, y minus z. And we have proven that if this guard holds, then both original guard in floating point and real arithmetic is going to hold. So this guard is going to hold both if evaluated in floating point and real arithmetic. And similarly, for the guard x multiply y minus z lower than minus epsilon, we will have that if this is satisfied, then the negation of the original guard is going to be true both in floating point and real arithmetic. For all other cases, so when our expression is between minus epsilon and plus epsilon, we don't know if the round of error is going to be is going to affect the evaluation of the guard. So in this case, we're going to emit a warning of a possible unstable guard occurring. So we have shown that if we get a result in our transform program that is not a warning, then we can be sure that we will get the same result in the original program. And we have also shown that all unstable guards and unstable computation that can happen in the original program are detected by our transformation. And we are going to meet a warning in this case. Of course, since epsilon is an over-approximation of the error, we can get some false alarm. So this means that we can have a warning even if the original program has no unstable guards. And yeah, so given a real specification, we have a way to define and to get an instrumented implementation of this specification in floating point numbers that soundly detect unstable guards. So it's able to detect all unstable guards. Now, through an example, I'm going to show you how you can generate the corresponding C code and how we can verify it in Pharmacy. So this is a function called TCOA, which is used in the detect and avoid library Daedalus developed at NASA. And this function is able to compute the time to coalesce of two aircraft, so when they are going to be at the same altitude. So given this real number specification, we can apply tau and get the transformed implementation. So here we will have ETCOA, which is the error, another approximation of the error of SC multiplied BC. And we're going to have the transformed function, which will say that if SC multiplied BC is lower than minus error, then we're going to return minus SC divided BC. Otherwise, if the expression is greater or equal than the error, we're going to return 0. And in all other cases, when we are between minus error and plus error, we're going to return a warning. So this transform function is printed in C syntax in this way. And besides that, we have to add some annotation, some information that helps us later in our verification. First of all, we need to define a function representing the real specification TCOA this way, and also a function, a floating point function that represent the naive implementation of TCOA. And here you can notice how the language ACSL, which is the specification language of Pharmacy, allows us to distinguish and to reason about both real number and floating point number in a different way. And yeah, besides these two functions, we also need a predicate called stable path that defines under which condition our program follow a stable path. So when unstable guards are not present. And finally, we are going to need a post condition. And the post condition says that when the result is not a warning, then the result of the transform program is the same as the naive implementation of the specification. And also that all the paths are stable, so we don't have any unstable guard. So it's important to notice here that here in this function, we don't have any value for the error. So the error E is completely symbolic, and we just said that E is an over-approximation of the difference between the evaluation of the guards, of the expression of the guard in real and floating point. However, in practice, we do want to know what this E is valued, given some initial ranges for the input variables. And to do so, we use Precisa and the global optimizer Kodiak in order to obtain a symbolic error expression and maximize it within some ranges. So in this way, we can obtain a numerical value for E, which in this case is 1.72 at E n minus 10. And then we can call the symbolic function that we defined before with this value. In this case, we will have to ensure that given SC and VZ between 1 and 1000, if the result is not a warning, then the difference between the result of our transform function and the initial real value specification is at most this number, which is the round of error of the transform function. So to sum up a little bit this part, Precisa takes as input a PVS real value specification and input ranges for the input variables, and generate a C implementation of the specification, which applies also the transformation tau to detect unstable guards. In addition, it generates some ACSL pre and post condition and some information about the round of error. Also, Precisa generates a set of PVS round of error certificates that ensure that these values that we use here are sound, so are sound over approximation of the round of error that happen in these expressions. So now that we have a C program annotated, we can use from a C to generate the verification condition that we have to prove in PBS. To do so, we are using the weakest precondition plugin of RamaC, and we have customized it to link in this way the floating point normalization we have defined for PBS and the Precisa round of error certificates. So to give you an idea of how verification condition looks like, we have this example. So the verification condition for the symbolic function tau tcoa is this first one. So if the result is not warning and E is an upper bound for the error of S multiplied V, then the result is the same as the result of tcoa implemented in floating point numbers. And this second verification condition tells us that if the input values are between 1 and 1000 and the result is not a warning, and also that this is a correct upper bound for the error of S multiplied V, then the difference between the result of our transform function and the real value specification is at most this number. So this instrumented C program is given to RamaC, which with its weakest precondition analysis generates a set of verification conditions in the language of PVS. Then we will use both this verification condition and the PVS certificates that Precisa has produced to ensure the correctness of the round of error. And we will prove in PVS that these verification conditions are correct. So it's important to notice here that even though PVS is an interactive theorem prover, We have defined some automatic strategies in order to be able to discharge these verification conditions produced by FromAC in an automatic way. And this is important because in this way, we do not require expertise from the user in the field of PVS or floating point arithmetic. So to conclude, we have in this work successfully integrated 3 formal methods tools in order to generate and automatically verify a C implementation of a PVS specification in real numbers. Our tool is available as under the NASA open source agreement at this website. And yeah, we have also applied this method to a significant fragment of the NASA formalization for Polycarp, which is a geofencing library, and Daedalus, a detect and avoid library. So we have generated actual C code from the PVS of these libraries. That's it. Thank you very much for your attention.